Welcome to this afternoon's deep dive discussion on semiconductors. I'm Wei from Homodeus Research, and joining me today, I'm privileged to have Rob Williamson, Managing Director of Alpha HPA, and YT Boon, a semiconductor specialist with an engineering background in microprocessor and ASIC chip design. Now, today's deep dive explores semiconductor industry trends, technology adoption, supply chain development, and the critical role of advanced materials in enabling next generation technologies. A few key topics that we'll talk about include the semiconductor market outlook, drivers of adoption, AI, data centers, and advanced electronic demand, as well as the role of high purity materials in semiconductor manufacturing. Now, before I go into the discussion, I'd like to provide a brief intro for our guests today. So firstly, we've got Rob Williamson. He's the Managing Director of Alpha HPA, an Australian advanced materials company, developing the world's largest single-site, high-purity aluminium materials manufacturing facility in Gladstone, Queensland. Rob's got more than 25 years of experience across the resources, technology, and advanced manufacturing sectors, leading the development and commercialization of critical materials projects.
Thanks,
Secondly, we've got YT Boon. YT is currently a managing director and portfolio manager at Nürnberger, managing several of the global and Asian technology portfolios. He's also a semiconductor specialist. Prior to financial investment, YT was a microprocessor and ASIC chip design engineer for about 10 years in the UK, Taiwan, and China. YT has worked at semiconductor companies such as ARM, Cadence Designs, Broadcom, Global Unichip, TSMC, and Huawei. So with that, I might just start the discussion. Thank you again, YT, and thank you, Rob, for being here today. So let's start with just setting the scene around the industry context. And YT, I might hand it over to you first, but can you give us a bit of a background on the broader macro on AI and semiconductor industry, CapEx trends, and why a slowing Moore's law is boosting the upstream materials market?
Yeah, Wei, thanks very much for the introduction and also connecting us with Rob and the team. I think what's very interesting to highlight is that we are seeing a rapid change in the semiconductor industry, especially over the last 6 to 9 months, because if everyone kind of go back to 2025. We've been through a rough year in 2025 with tariff, trade tariff-related issues that disrupted the whole supply chain. While at the same time, global investments into artificial intelligence infrastructure continues to accelerate. But that also meant that the semiconductor industry had to spend some time to reconfigure the entire supply chain, be it from the upstream to the downstream in semiconductors. What that meant was in 2025, while global AI infrastructure CapEx was very strong, and it's even stronger in 2026 and going forward in 2027 as well. If we look at just broadly, US AI infrastructure spending by the 4 top hyperscalers or cloud service providers, we're looking at over 70% increase in these AI infrastructure capex. Be it Google, Microsoft, Meta, everyone is now increasing their capex, and all these capex eventually flows into the semiconductor industry. Now in 2025, because of the supply chain disruption, the whole industry had to deal with that supply chain reconfiguration. Now in 2026, starting from around late 2025 and early 2026, the semiconductor supply chain finally gone through that reconfiguration and really started refocusing on innovations within their core technologies. And this is where we're now starting to see a lot of innovations within the material side of things. As most investors probably know, most people in the semiconductor industry has probably known that the Moore's law, which has been guiding the industry in terms of its technology migration, has been slowing down because the technologies required to shrink transistor geometries is just basically hitting a lot of physical limits. What that means is a lot of the innovation for next generation semiconductors had to do with materials innovations. And this means that a lot of higher purity materials are required for the next generation technology, particularly if we look at logic semiconductors and memory semiconductors. Now, because of a lot of these, originally what we thought was, kind of like time delay was actually supply chain reconfiguration. But now the industry is back focusing on material innovation itself. If you talk to the TSMCs of the world, the Samsungs of the world, or even the material suppliers in this industry, they're now really, really focusing a lot on both the equipment side of things to drive the next generation technologies and also on materials. So in my line of work today, I talk to a lot of semiconductor companies and upstream materials companies. Over the last 9 to 12 months, I've been hearing a lot more discussions about next generation technologies, be it in advanced packaging or be it in the wafer front end processing technologies. And one of the key things that we keep hearing is how do we increase purity? How do we make sure that, with the more complex semiconductor steps or processes, cleaning processes are becoming more complicated. How do we purify the entire supply or the steps to make sure that we are able to, continue to shrink the entire geometry in a very different way? Because as most people may have heard, EUV or extreme ultraviolet technologies also hitting a limit because of various economics and things like that. So I think the next big thing within semiconductor innovation lies a lot on both the equipment side and also the material side of things. There's been a lot of new innovations. In the past, we've probably only heard about wet cleaning process in semiconductors. Now we're hearing more advanced solutions like dry cleaning, which is a completely different ways of processing semiconductors. And this means that we need better and different kind of materials innovations. And I think this is just the very beginning.
Great. That's a great introduction. Thanks, YT. And just to set the context for this, are you able to give us a sense as to this shift in terms of the high purity materials? When did you start to notice this trend?
Yeah, so obviously, when it comes to materials, there's a lot of different types of material substance, and the semiconductor supply chain and the different steps are quite complicated. But I would say over the last 3 years or so, when we speak to semiconductor equipment companies, they started to talk up more about next generation materials innovations. And about something like around 3 to 4 years ago, TSMC, for example, has started to talk more about their back-end innovations, especially in advanced packaging. 3-4 years ago, we started seeing CoWoS, chip on wafer on substrates, being adopted for advanced AI chips, because these GPUs or CPUs that we know of today for AI applications are increasingly more complex. Having them on a single wafer doesn't work anymore. You have to package several wafers together. And this also makes the back-end assembly or advanced packaging process more complicated. And this also involves a lot of materials innovation. And this is on top of what I mentioned about wafer front end. So to give a bit more context, around 3 to 4 years ago, Tokyo Electron, one of Japan's largest semiconductor equipment maker that works very closely with ASML and also working very closely with TSMC. started talking about 3 nanometer and 2 nanometer in different types of architectures, where the key players in this market are exploring different type of materials. As I mentioned about wet cleaning, dry cleaning, that's just one aspect of things. They're exploring different methods, and this requires different experiments on different types of materials. And as you can imagine, with these 2 or 3 nanometer technology process that are dealing with subatomic level type of precisions, the purity of the materials involved in terms of just washing, cleaning these wafers requires very, very high purity materials. Just the water alone that's used for cleaning wafers are not the typical water that we drink, because the typical water that we drink may look clean, but it's extremely contaminated when it comes to the semiconductor process, because it still contains a lot of particles. So if you think on that level, subatomic level type of applications, you'll see that we're increasingly relying more on very highly precise materials that is very highly pure, even just for the cleaning process. And on top of that, when it comes to back-end or advanced packaging, including what we know of today, the high bandwidth memory packaging processes. These are highly complicated as we stack more layers of wafers together, and when we package them in a cavity with different types of processes involved, the materials that we use for these type of cavity within the semiconductor package are completely different from what we used to know of. And so these involve a lot of different materials. I think obviously we have an expert here on the line, Rob.
Yeah, I might give Rob a go very soon. Just a few things to clarify on. The first one is this trend that we're seeing. Is it an AI trend, or is it beyond AI? Is this something which is because of the advanced node, or is it just like a AI thing, and if AI falls over, then it's game over?
I think it's a combination of both. The reason why we are moving along much faster, the innovations that we're seeing in the semiconductor space are accelerating, is because AI is driving a step change, a massive step change in the way semiconductor processes are being dealt with. And the second thing is, even without artificial intelligence, the world's been very, the world has started dealing with a lot of material innovations when it comes to semiconductor, when it comes to particularly when it comes to like automotive, different types of applications, space, for example. But AI is just boosting the timeline. We need to get a lot of these things done very quickly.
Excellent. Okay. This one I think is probably a good question for both of you, but it comes down to zero alpha emission. So that's something that we hear come up quite often in conversation. Maybe just a sentence or two from you, YT, as to how important this is. Is it a nice to have, or it's something which is critical? And then after that, I might get you to follow on, Rob, and give us a bit of an explanation about what it is and how you play into zero alpha emission. Thanks.
Yeah, I think there are actually, when it comes to the next generation semiconductor process, there are a lot of new buzzwords. One of them, obviously, is being zero alpha emission and all that. It's a very critical aspect that I would say involves various types of semiconductor aspects. Different steps of whether it's within front end or within the back end of advanced packaging. But we have an expert here who can give us a bit more color on that. And I'm actually also very interested to hear from Rob what this actually means to the whole industry.
Excellent.
Yeah, well, first of all, YT, I just want to say that everything you've said I'm in full agreement with in terms of your take on the market, and certainly it tracks with the trajectory that we've seen in terms of the uptick and level of interest in our sort of high purity materials essentially for those markets. And I think in the context of Moore's law, like that you were talking about, which is for those that aren't quite up to speed on that, it's the idea of a doubling of computer power every 2 years. That's what the original Moore's law was, and of course now it's decaying a little bit. But again, I think it's the same thing. I think the focus is definitely on heat and how you can remove heat as part of the story, and what you do that with comes down to a material, and that's certainly where ours comes in. In terms of zero alpha or low alpha emission materials, we absolutely see that as a key demand. And in fact, I was in Taiwan a couple of weeks ago and talking to obviously a very sophisticated customer base there. They are fully across the specification for that, coming directly out of TSMC. There's no question in my mind that, and in theirs, that this is a sort of a hurdle that any material supplier into the advanced package that YT is referring to, you have to be able to meet. And so it's about removing heat, and it's about doing so with a material that does not impact the chip's productivity, which is what alpha radiation can do, or does do, if it's present. So that is a absolute certainty from our side. And what I actually saw in Taiwan was just further opportunities for the adoption of materials such as ours into that advanced package. There are still a number of locations in the package on the CWOSs, the CoWOS, I should say, as YT is calling it, where there is still silicon being used. Anywhere where there is silica, there's potential. I think there's some upside maybe where alumina could be adopted, simply because has the similar mechanical properties whilst being 3 times, 4 times more thermally conductive, depending on the application, and even more so if it's a more homogeneous material. So plenty of upside there, and as I say, the criticality of that low alpha or zero alpha emission specification when you're on the advanced package is an absolute requirement.
And so, Rob, you're really talking about the thermal fillers here. Is that correct?
Well, it's actually, in that case, yes. Anything that is simply that will be part of the actual advanced package when it's finished. And when we talk about the advanced package in real simple, my mechanical engineering terms, it's a high bandwidth memory, it's the logic chip, which is the NVIDIA design chip as an example, or the TPU, or whatever it is that whoever's technology you're talking about, that then is all sort of mounted in one sort of unit, if you will, that then is integrated into the broader sort of GPU accelerator unit, so to speak. And anything that sort of is in proximity to that has to be low alpha. So as an example, tin, which is the little solder balls that they make, that is actually the electrical interface to the package onto the main circuit board, that has to be low alpha. So it's just anything that's in a vicinity of that package is critical to be low alpha. So
right. And YT, back to you, just in terms of the semiconductor material cost stack. Are these low value commodity inputs, or are they increasingly strategic?
I think they've become more strategic over time. When I was a microprocessor chip designer around 15, 16 years ago, materials or various types of materials for semiconductor processing is deemed kind of like a commodity. But over the years, things have evolved very quickly. And especially over the last 3 to 4 years, I've seen a massive step change. Like what Rob mentioned, just on the thermal side of things. Because chips today, semiconductor chips today, like the HBMs or the CoWoS processes, they're stacking different wafers together. And that makes heat trapping easier. That means heat dissipation becomes an increasingly problematic thing. Now, when it comes to AI applications, As most of you know, GPU consumes a lot of power. That also means that it needs to dissipate a lot of heat. Now, if these heat are trapped, and if they're using materials that are trapping these heat, even in a more severe way, that means the whole device will break down very easily. So what we're seeing is at the very beginning, when very advanced AI GPUs were produced, they were attached with a lot of external thermal cooling solutions, devices to help cool it down much quicker. But that only solves a certain portion of the problem because it is very imperative to actually make the advanced packaging process itself using materials that can dissipate heat or doesn't create those heat so quickly. So the whole industry over the last 3 to 4 years has started learning that, okay, there's the old ways of dealing with these materials has to change. I also mentioned about wafer front end, which is very different from what we're talking about within advanced packaging. That's at the very beginning of the wafer processing stage. That's also seeing a lot of innovations in materials. And I think that's another area where if we look at how these materials companies have evolved over time. In the past, you would see, tens or hundreds of very small materials companies, say in Japan. You would find tens of different semiconductor materials companies. Each one of them are like a micro cap or very a small cap. But over the years, they've all consolidated. Just as an example, a company like Resonant, which was a combination of, I think, 4 to 5 different semiconductor materials companies, have evolved to become a much bigger company. And with these type of consolidation of the industry, a lot of the materials companies are now innovating a lot faster. And they're adopting a lot of new technologies and working more closely with the semiconductor foundries, the memory chip makers, to advance into the next generation technologies. And with this type of consolidation, industry migration, we're definitely seeing massive change in the dynamics of these type of materials companies.
Right. And so just to give us a bit of sense as to who are the incumbent suppliers and who's Alpha, potentially looking to displace or competing against at this point in time.
Well, I mean, we can't name our customers, but I think it's the main, replacement that we are actually bringing to the party here is that we're replacing is silica. So silica is the dominant material, and it's been successful in that application for a long time because, and I think as YT rightly pointed out, it's been somewhat semi-commodified. Is because it was mechanically stable and did a mediocre job of extracting heat. But when you're talking about a 300-watt GPU from 5 years ago, that was okay. But we're at 1,000 watts now for GPUs. That's like a space heater in your bathroom. Silica just doesn't cut it. And so that's sort of really what's happening. But in terms of our customers, what they're doing is they're just converting their equipment to run high purity alumina to spherodize into fillers for this application instead of silica. So they've kind of got a bit of optionality. So we're not necessarily having to sell this to any of our customers in that context. We're actually, we are all effectively working in the supply chain in concert with the demands from the likes of TSMC, SK Hynix, Samsung, Micron to service the CoWoS package that TSMC is assembling.
Right. And YT, you mentioned before that a lot of these Japanese companies, they've kind of consolidated and they're quite advanced in their materials now. Rob, we saw last quarter 2 of the Japanese customers upgrading their LOIs quite materially. Can you talk about what has been driving this upgrade cycle?
I think it's just as the adoption of the high purity alumina for that thermal management issue continues to come through, they're getting their qualification done through that supply chain, like I referred to. So a lot of the Japanese guys are supplying through to essentially ultimately into that TSMC direct supply chain for the logic chip side. The Koreans tend to be more into the high bandwidth memory side, although the Japanese do supply into that a little bit as well through their customers, which are companies like Nagase, Namix, Resonac that YT mentioned earlier, Sumitomo Bakelite. They're effectively our customer's customer. So that volume uptick though is really just a reflection of, as they're qualifying more and more materials through that supply chain, they're upping their LOI requirement. The other thing that's happening that we're seeing is, an example is a company in Korea, one of the larger end of town. It's almost like an adoption curve in terms of a recognition from the industry that, the bigger end of town sees the opportunity. They then want to go into this as well and recognise that they'll be left behind if they don't. And so there's a business in Korea, quite large. They're investing capital to build out more capability for spheroidized alumina. And they're fast tracking a qualification with us at the moment, but they're expecting, or they're building a 1,200 ton facility. And so I can't say who that is, but that sort of speaks volumes to how the industry is being seen now in terms of the adoption of this material to manage heat in these advanced packages. You've muted yourself.
Sorry, thanks, Rob. So you touched upon it a bit there, but are you able just to give us a bit of color on what the qualification to commercial order pipeline typically looks like in terms of time and conversion rate?
Well, so the first customer we actually engaged with on this was probably the Rolls Royce of this type of material, a group out of Japan, and that was December of 2023 when we actually first started talking to them, and they've upgraded once already, and that was one that you referred to. They've tripled their volume. We fully expect them to double from here again in the next sort of few months' time. But they're like the sort of bleeding edge of this, and some of the material that they make is actually going to liquid underfill, which is extraordinarily valuable material. But others have been sort of, that's a longer version, in terms of the qualification. Others have been quicker, sort of 12 months to 18 months. But we're fully expecting now, as time pressures start to build with that business I mentioned earlier, we expect to get that done within the next 6 months. But that's just goes to show how, depending on what part of the cycle some of these businesses are entering into, their relationships, how quickly they can push it through.
Okay. And just to round out the whole supply chain, are you able to, this is a bit left field, but are you able to explain alumina, Rio, Orica, and how that works?
Yeah, absolutely. So in terms of our flow sheet or our production process, there's really, I think, first of all, it's a performance-based material. So there's no connection to any market. There's no index on the sales price of our material. That's number one. And number two, the relationship with Orica that we have here is in terms of them providing chemicals that we use in our technology to produce this particular specification of product and that's in our solvent extraction technology. That is a naturally hedged input, so we're not really exposed to any commodity cycle on that side. And then Rio and by the way, Orica is a 5% shareholder in us. They've done the technical DD and they understand the business. Their CEO is an ex-BASF chemicals guy and understands the semi market. But then separately, Rio really they just supply the aluminium units as we call them, and it's just our technology is able to take advantage of a upstream semi-refined aluminium, or it comes from an alumina refinery. It's not actually finished alumina; it's alumina hydrate, and that stuff's about nominally $400 a ton. And of course, we're selling our material on average for 29,000, 30,000 US dollars a ton. So they just provide the units there. And so but the main important connection that we have is with Orica because it's by pipeline. We're connected directly. There's about 200,000 tons that goes between us and Orica over the course of 12 months when we're in full operation, whereas about 13,000 tons a year comes from Rio's side. But it's all within a 2-kilometre radius of the plant.
Excellent. That makes a lot of sense.
Yeah.
I might just jump back to you, YT. In terms of the Alpha's technical story on solvent extraction producing genuinely differentiated purity, does this hold up against what you'd expect from a credible new entrant into the supply chain?
Yeah, I think let's put it this way: the semiconductor material supply chain is quite a different supply chain, given it's got many layers of players involved. And there are a couple of new drivers that is enabling a lot of changes in the types of materials at different layers that we're looking at in the supply chain. So when I look at the broader industry, a lot of new types of materials, not just high purity type of materials that we're speaking here. There are various types of new materials that are being introduced to the industry, and we've just talked about some Japanese, some Korean material suppliers, which are kind of like more downstream compared to what we're talking about here, and we're seeing different layers of materials companies are now developing different solutions. One of the key drivers we've mentioned, thermal cooling, right? Because this holds a completely different equation, when it comes to the thermal coefficient and things like that. Another area that we're looking at in terms of materials is in terms of the processing steps itself. There are different types of materials that are now being developed, as I just mentioned, just on the cleaning process. A lot of new types of materials are being developed. Obviously, this is very different from the high purity materials that we're talking here, but it all goes into the same direction. Whether it's AI, artificial intelligence that's driving up the thermal cooling requirements and things like that. And a lot of innovations has been taking place. Rob mentioned about Sumitomo Bakelite, which is actually a Japanese semiconductor material vendor that was actually quite focused on automotive semiconductor chips. Now, automotive semiconductor chips are quite different when it comes to chips that we look at that goes into data centers or consumer electronics or laptops. Automotive chips have to deal with high temperature and also vibration. Now, our normal mobile devices or data centers don't deal with these type of mobile vibration kind of situations. But when it comes to AI applications today, even though we're not dealing with the same type of vibration, the industry is now also moving towards this direction. Why? Because a lot of the data center applications now finds themselves shooting into space. Space, there are a lot more Cosmo type of things that they have to deal with. The coefficients are completely different. So we're finding a lot of new entrants into the space. A lot of these semiconductor materials companies, packaging materials companies are now dealing with a lot more type of materials. The traditional materials that they are used to are no longer viable. And a lot of these material vendors are finding themselves looking at more types of applications. Their automotive applications that they used to develop are now being used for AI, and now it's being used for space type of applications. I think a proliferation of types of applications are driving a lot of new entrants into the space.
And
I would just add to that, like we're seeing that in real time too, in terms of, mobile onboard local AI processing capability that is starting to emerge in the sort of product roadmaps for the major manufacturers. And so that, to the back in what YT's saying, the adoption of even having on mobile, AI processing capacity is important. And so they've got to solve for the heat, but it also needs to be mechanically stable, which does rule out certain materials. And we're absolutely seeing that. And of course, the same when it comes to, autonomous driving, that's sort of being enabled through AI even more. And yeah, you get back to that same place. So it's everything comes back to the same support.
And to be clear, your materials are safe.
Yeah, it's sort of where that technical trade-off has taken place with, we've said before, like there are other more thermally conductive materials out there than high purity alumina, but they have other issues in terms of their compatibility from a mechanical stability point of view, or in the case, and particularly in the case of epoxy molding compound and encapsulant material, anything with like a nitride, like a boron nitride or a silicon nitride, is actually incompatible with the epoxy resins, and so they can't actually even be used in that application because they'll react and essentially destroy the chip. So that's not even an option.
Right. And YT, you mentioned there's a lot of kind of like new materials being explored at this point in time. Just in terms of the stickiness for semiconductor material qualifications, once the supplier is locked in, what's the switching cost or risk for an end user?
Typically, when it comes to semiconductor engineering, once a material's qualified, it's very sticky. The cost of changing is actually very high because qualifying a new type of material actually takes sometimes up to years. And that means tens of millions of dollars are being spent to make sure that that particular material is going to be used for a lot of different types of applications. So like what Rob mentioned, silica has been a very stable material that was able to solve a lot of problems in, I would say, the older generation semiconductor. But it's been used for like at least the last 30 to 40 years. Now, we're seeing more newer types of materials are now coming on board. But the whole idea is that, a higher mix of different materials, and each of them are kind of like, very sticky because they're all applied to a very different application itself. And what that also means is a proliferation of different types of innovations in various types of applications. Now, memory chips are very different from logic chips. The advanced packaging in high bandwidth memories are very different from the logic chips that the GPUs are being built on, the chip on waveform substrate process. And in the future, there are newer processes because we're not stopping at just HBM. HBM is now evolving into HBM4, HBM4E, HBM5 is coming in the next few years, each stacking more layers of memory wafer chips. And these memory wafer chips are also evolving very quickly. So there will be a higher mix of different types of materials, and each one of them are addressing a specific use case. What that also means is that they don't typically want to just introduce new materials. New materials are also not necessarily very stable. Once you find a solution, you want to stick to it and amortize it over time. We've seen that across various types of electronics materials industry. And as I mentioned about the industry dynamics, in the past 10, 20 years ago, you have a lot of small mid-cap electronics, semiconductor materials companies. Over the years, they've consolidated. Each one of them are developing, more innovations. And today, compared to say like 5, 10 years ago, there are a lot more larger cap materials companies. Now you have in the US several electronics materials companies, in Europe as well. In Asia, there are increasingly more numbers of players in Japan, South Korea. But what's also interesting is that if you look at China and Taiwan, China's developing their own processes as well, which is quite different from the rest of the world. And because they don't have access to the best equipment like the EUV, they have to rely on innovations within materials. And I think that's another area of opportunities for materials companies within the region. And there's also a trend of localization in semiconductor materials. And why is that? Because a lot of the semiconductor companies have gone through a lot of supply chain disruptions over the last 5 years. Initially with COVID, that disrupted the whole value chain. And later on, we have geopolitics that obviously led to tariff wars and so on. And that also made a lot of the semiconductor material suppliers and their customers quite nervous about the supplies of these materials. And very lately, I'm sure everyone's been hearing about, rare earth export controls and things like that. Obviously, that's impacting a different part of the supply chain. But all these are coming back to the need for localization of supply chain, and especially for semiconductor equipment and materials. Because having these materials domestically ensures the stability. For example, we're seeing that in China, we're seeing that in Japan, in Taiwan. TSMC is working with a lot of local suppliers in terms of trying to localize their supply chain of materials. The Koreans as well. The Koreans are very advanced in terms of like trying to localize the supply chain. Hence, there's so many Japanese and Korean material supply vendors. I think that's also another aspect that is quite fascinating.
Is that a risk for A4N then, in terms of the localization and them not being a local?
Well, I think the thing is, it's to think about. I mean, so firstly, all those nations that, with the exception of China, I guess, are all kind of allied partners, geopolitically speaking. But it's worth noting, and I certainly came across a bit of that thematic in Taiwan a couple of weeks ago. But it's more so in what you would call the midstream step, as for what we're seeing. So that is to say, people that are making the spheroidized alumina, or people that are making a sort of an already manufactured material with a raw material that they get from us or from whomever else it might be, or for whatever the thing might be. So the raw material is coming from a jurisdiction such as Australia. They're then producing the spheroidized alumina in-house, and that's that sovereign piece that I think is where the main focus is, as opposed to going all the way back to the mine or some other, which is even a bit past us, that they're sort of more focused on what I would call the midstream. And so, to YT's point, Korea is building out and already has spheroidized alumina capability in the country, as does Japan, and they're expanding that capability. As an example, a lot of those companies were sourcing their aluminas from China. Or even there is some spheroidizing capability. So Novaray is one of the big Chinese companies, and Novaray is a big spheroidized silica supplier already into those markets that we've been talking about. And certainly TSMC and others are wanting to break that linkage, although, the price has been good, of course. And we've actually been in situations where we've been working with a customer where we know they were supplying or sourcing aluminas from China, and then that we spoke to that customer, not realizing that at the time, and then we kind of worked out inadvertently that we would have been supplying our customer's customer through a China portal, and we've not pursued that. And in fact, we know that there's no requirement for our kind of specification material for an internal domestic Chinese chip at this stage. And so we actually steer it clear from the Chinese counterparties, because we know they're just clipping a ticket to send it on to Japan and Korea.
Right. Okay. That's good to know.
Yeah.
But I guess back to the original point, to your point, YT. So qualification is actually, once you're qualified, you become a very sticky, part of the supply chain. Rob, can you remind us where is Alpha in terms of the qualification process?
Yeah, so it varies, and like I said, we're already qualified for some because we have binding agreements now, right through, and that just means that as the scale and capability of Alpha grows, so does the adoption through that market. And we've got other customers that we've just commenced qualification that are looking, they're looking to build out a 1,200 ton capacity in the future. There's others that are essentially we're already qualified with, and we're selling to them in Korea as well. So we're at varying stages with various companies, but we know that it's happening in terms of that adoption. And to YT's point, it does take time because it's got to go through that supply chain. And I think now A4N is getting a bit of brand recognition within some of those markets. We've obviously done a lot of work around that in terms of trade shows and things like that. But I think there's also a bit of brand recognition coming through in terms of people recognizing our capacity to solve for the low alpha emission problem, and therefore enable the adoption of aluminum to manage heat in these advanced packages.
Right. So a couple more kind of like thematics that I want to touch on. One is just the competition landscape and the moat that you might have. So YT, for you, who across the research that you've done are the realistic global competitors capable of matching Alpha's purity specs at scale, if you've come across any, and what's the barrier to entry to them catching up, in your view?
Yeah, to be honest, I have not done very extensive research that allows me to find another play in the market that has the same type of credibility, even the planned capacity to be had. So I think at this point of time, or over the last 6 to 12 months, I've been speaking to the midstream and the downstream players more, and they are also telling us that it's quite hard to secure supplies. Because for a lot of these midstream, downstream players, for them, it's the capacity and also the stability of their suppliers. And they have to go through a quite long-winded process of qualification, and they have to deal with their customers' and their customers', which is quite a lengthy process. We've just mentioned like at least 4 to 5 different layers. Yes, NVIDIA or AMD or Intel, Samsung, SK Hynix could be the end customer, but in between, you're looking at least 3 to 4 layers of players, each one of them trying to qualify for a specific step. And whether a material or whether a specific new process works, it just takes at least 6 to 12 months. And if you multiply the number of layers, you're looking at years here. And none of these midstream or downstream players want to change the suppliers. They want to start with someone that is having that credibility and the capacity, because that's usually what it comes to. Because if you think about an end customer like a TSMC and then NVIDIA, the first thing they want to know is, wait a minute, you have a very innovative solution, but do you have enough capacity? Because at the end of the day, you got to be able to produce. In terms of the number of chips, we're looking at millions, and that means trillions in terms of the type of numbers you're looking at from the upstream. Because for every layer you go down, there is a yield thing that you have to deal with. So it diminishes throughout the value chain. So it's a very complicated and long-winded process. I think some investors or some people will be quite familiar with other industries like battery materials, right? And you don't experiment, you don't use you're not changing the materials very quickly from time to time. Yes, there are certain smaller portion of the material innovations that you'll see over time to enhance a specific process. But it's very similar in the semiconductor industry. But when it comes to a very large industry like AI chips, GPU chips, high bandwidth memory, it all boils down to the different layers, and it always comes down to capacity and stability.
Yeah. So it sounds like, to your knowledge right now, there hasn't been any large competitors that you've come across as part of your research yet, and it sounds like Alpha is pretty entrenched in terms of the whole process at this point in time. Then,
Yes.
yeah. Well, I'm just conscious of time, so I think we might just wrap up soon.
What I could just quickly comment on that way, just to say that our competitors in the context of what we do for thermal filler, one of them would be another business called Sumitomo Chemical. And we know from first-hand information in speaking with them that their capability to meet the zero alpha emission specification isn't actually there. It's not bad. It's probably the best available on the market other than ours. But we're a factor of 10 better than they are. And so I think, again, it just speaks to the fact that we're building that credibility is there, and we can deliver that lower spec, which is just unlocking the use of this material in a material way.
Excellent. Just a couple of quick more comments from both of you. So if we say that AI capex growth moderates in 2027, hypothetically, how exposed would Alpha's demand base be versus the more structural drivers?
Do you want to go, Y2?
Yeah, first of all, I might be a bit biased. I don't think the global AI capex will slow down in 2027. I think it will maintain a pretty solid growth phase. And in fact, I think we might not even complete a lot of the AI infrastructure build out that was originally planned for 2026. The whole semiconductor industry is now experiencing a lot of bottlenecks in a positive way, that the whole semiconductor industry has not anticipated such a surge in demand. And it takes time to build a capacity within the semiconductor value chain. And over the last few weeks, we've started hearing a lot of new semiconductor fab expansion plans. And if you really look into the details, a lot of these new fabs will be ready 2 to 3 years from now, if there's no delays. And typically, we've seen a lot of delays in terms of the building constructions and so on. So I think it will take time.
When they need HPA, right? After it's actually built, rather than
exactly. So as they build out these new fabs, these are all the newer technologies that need higher purity materials, like from HPA and so on. I think I'm not too worried about that, short-term volatility. I think, as I mentioned, capacity and stability for the whole industry is more important than just.
I was going to say that makes a lot of sense. And Rob, if you have any comments in regards to where you think that the demand lies and whether it's a one-trick AI pony.
Yeah, I mean, it's again probably not the most unbiased take on things, given the fact that we stand to benefit from it. But I think there's a good analog to this is NBN infrastructure. So if you go right back and to when sort of broadband was rolled out, there was an excess in capacity at the time. The big companies, AT&T, Telstra, what have you, went to spend a lot of money. But of course, there was at that stage there was a bit of excess capacity, but they knew that if they didn't do it, that they would be left for dead in the end, and that's that's what happened. And obviously now we're still way short on bandwidth in terms of data transfer. And if I think that is a really sort of interesting way to think about what's happening in AI hyperscalers, where these businesses like Microsoft, Meta, SpaceX, etc., they don't really have an alternative. Like if they don't do this, then they won't have a business in 5 years time. So whether, say what you will about how or what AI actually looks like for you and I as human beings running and operating in our day to day, the capacity to run AI has to happen, because if it doesn't, that those companies will die. So I think that's sort of how I think about it. So that the momentum's going to continue.
Excellent. That's a great explanation. So one last question for you, Rob, before we wrap up. What's the single metric investors should be watching each quarter to track whether this thesis is playing out?
Sorry, which is playing out?
Just the thesis of investing.
Oh, yeah, sorry, yeah. No, I think obviously there's a couple of things really. I wish there was just one simple one, but there'll be more announcements in terms of our commercial side of things, which is to say letters of intent. Even though we're well over 100% of capacity, I think we're at 118% capacity of the plant right now under letter of intent. We'll continue to extend that, and that just drives commercial tension with our customers as we encourage more to put their foot on it. There will be some more binding contract announcements that will come up in the next six to 12 months as well. That'll follow in conjunction with that, and then of course just the ongoing capex build out that we're doing at the moment, and that's going quite well for us, starting up towards the end of next year. I think the other big overhang in the market right now is a view that we will require additional capital from somewhere to finish the build, and that's just a matter of us unlocking the debt funding from the government, and we're supremely confident that will happen in due course. So it does create quite the buying opportunity if you believe in management and what we're doing.
Perfect. Well, I think we'll call it there. YT, Rob, really enjoyed the conversation. I learned a lot, so thank you for both of your times.
Thanks, YT. Thanks, Wei. Well done.
Great. Thanks, guys. Thank you for joining. Bye.
Bye.